Hi everyone, and welcome to the next lecture devoted to the family of Hall effects. So today we will speak about anomalous Hall effect, spin Hall effect, and inverse spin Hall effect. But before we will go to the all this interesting spintronics phenomena, let me briefly remind you what is normal Hall effect, classical one, which gave a name to the family of all other effects. And as you already know from our previous courses in experimental physics, Hall effect is, you can observe, for example, in such sample of conductor, so it can be metal, non-magnetic metal, copper, silver, whatever you want, or it can be also a semiconductor. Then when you apply a difference in electrical potential, you will get current. So pay attention that here current finally propagates in the proper direction, like defined by engineers, for example, which means in the opposite direction to the motion of electrons themselves. And so electrons are moving here to the left side, and you will get access to the Hall effect if you will apply a magnetic field with inductance B, for example, like it's shown in this case, perpendicularly to the plane of your sample along that direction, and current, so electron flow propagates in minus x direction. What happens in this case? There will be a Lorentz force acting on the electrons or on the holes, if you're speaking about semiconductors, which will act perpendicular to the velocity of your electrons and perpendicular to the field. So in this case, it will bend electrons in this direction. If your sample is limited in space, so it's not infinitely wide, then what happens, these electrons will start to accumulate here at the transverse direction. And moreover, they will create a new electric field, which will be acting against this motion of electrons. So at the end of the day, we'll come to the steady state situation when this Lorentz force and motion of electron to this side will be compensated by the electrostatic potential, which is accumulated already at the edges of your sample. How you can describe it? So here we are coming back to the equation with which we worked already. So in Sommerfeld model, so here is a shift of our Fermi sphere when we apply electric field E in this direction, X direction. And the difference is that in addition to this force, we will have this term, which is a Lorentz force term. Yeah, so this F, it's a sum of all forces, which you have to take into account. And now, in addition to this electrostatic force, we are taking into account also the Lorentz force. And afterwards, you just make a few tricks. First of all, what you can do, you can come from your quantum mechanical momentum, HK, you can move back to the linear momentum, like in classical physics, MV. Here, and second, what you do, you consider a steady state when you have already some field across a sample, and electrons do not accumulate anymore because there is already some accumulation. So in this case, you can say that this derivative is equal to 0, and having this, you will get simplified equation. After what you do the following trick, you just split it into, you project it onto 3 axes. So when you will project it to the x-axis, you will get here projection of Vx, and then there will be an applied electric field x coordinate, and here because of cross product, you will get component of velocity if y. And then you can get similar formula for Vy for velocity in this direction, and then there will be component for the velocity in that direction, so transverse to the field. Having this, we do the next very little trick. Since we are speaking about steady state, we do not have any more motion of electron along the y direction, because Yeah, because electric field is blocking it, so it's compensated already with Lorentz force. That's why what you do, you just replace this Vy with 0 in both these equations, and then you can define a velocity in the x direction from this equation. Here you have it already. Just make one equal to another, and this brings you to this very simple formula where you can get the value for electric field in the y direction. So this is whole field as a function of the applied electric field in the x direction, which triggered our originally our current, and here stay in the cyclotron frequency, which we have seen already. So it depends on applied magnetic field B, on the relaxation time tau, and on the effective mass of electron or holes m. Good, so this is the important equation which defines as the electric field created by the Hall effect, and then we need to introduce the parameters, and the first one is named Hall coefficient, and it measures the field along y per unit applied current and magnetic field. So it means that you take this electric field component y and you normalize it with electric current x along and with magnetic field b. And yeah, if you will then plug in the value for ey, this one, which we obtained here, and x, we have seen this formula we used when we were talking about classical conductivity and resistivity. This is a just standard formula for electric field. This is Ohm's law. When you plug it in here, then you see that this Ex disappears, then this field B disappears, and you will get very simple formula for the Hall coefficient, which is -1 over NE, where N is the density of electrons. It means that you have this Hall coefficient. It's principally characteristics of your material, because you see there is no any external field applied of electric or magnetic. This really describes your material, and the most important, as you see for the Hall effect, is carrier concentration N. And if to go make a step further, we can memorize that in semiconductors, the density of carriers is smaller. It means N is smaller. That's why Hall effect, which is inversely proportional to N, is larger. That's why semiconductors are used in the Hall sensors. And now I would like to introduce two more parameters, which we will need also later. So first of all, specific Hall resistance, which you can find as ratio of this Hall electric field divided with current. So without magnetic field, so resistance you can find then as a Hall coefficient multiplied with applied magnetic field B. And there is also such important parameter as Hall angle, which you can define in the following way. So tangents of Hall angles is equal ratio between y and x component of the electric field. And this one, then you can find that tangents of Hall angles proportional to the conductivity of your material, proportional to the Hall coefficient, and proportional to the applied magnetic field B. So we will need Hall angle, for example, when we will speak about spin Hall effect, because there is a spin Hall angle which also defines the efficiency of your effect. And in this slide, I would like to show you this table taken from the Kittel solid state physics book, which describes you the values of Hall coefficient, experimental and calculated, and in CGS units, 10 to the power minus 24, for some selection of materials. So here you see this alkali metals, and Hall is -2, -2.6. And then if we go on For calcium, it's a bit more. For barium, even better. And then arsenium is huge, yeah. For bismuth, it's huge. And what I would like to attract your attention here to the fact that here, for some of the elements, like for example, aluminum, the whole angle changes its sign. According to the simplest model, like we discussed here, as long as you work with metal and your charge carriers are electrons, not holes, you should expect the same angle of Hall effect. And nevertheless, as you can see here, a normal metal can change even the sign of Hall angle, which is very interesting. And the reason behind is that, for example, aluminum is complex material with 3 valent electrons and this complex band structure. Therefore, in some cases, it can behave because of this complex band structure as semiconductor. So we can speak about effective conductivity by holes behavior. So this positive Hall angle can be explained in terms of energy band. So this is not of importance for the course of spintronics advanced materials, but just keep in mind that energy band model is really powerful and it can explain even such a unexpected behavior of your solid body. And before we will move on, let us have a break and watch a bit how Hall effect sensors work. So principally, Hall effect is one of the most popular, probably used nowadays sensors for magnetic field. And here, just very basic video to get a bit closer insight into the real application.
Hello, Dan Nelksky here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and the Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of only few microvolts per Gauss, so therefore these devices are usually manufactured with built-in high-gain amplifiers. There are two types of Hall effect sensors, one providing analog and the other digital output. The analog sensor is composed of a voltage regulator, a Hall element and an amplifier. From the circuit schematic we can see that the output of the sensor is analog and proportional to the Hall element output or the magnetic field strength. These type of sensors are suitable and used for measuring proximity because of their continuous linear output. On the other hand, the digital output sensor provides just two output states, either on or off. These type of sensors have an additional element, as illustrated in the circuit schematic. That's the Schmitt trigger, which provides hysteresis or two different threshold levels, so the output is either high or low. For more details how the Schmitt trigger works, you can check my particular tutorial for that. An example of this type of sensor is the Hall effect switch. They are often used as limit switches, for example in 3D printers and CNC machines, as well as for detection and positioning in industrial automation systems. Another contemporary applications of the Hall effect sensors are measuring wheel speed or RPM, as well as determining position of crankshaft or camshaft in engine systems. These sensors are composed of a Hall element and a permanent magnet, which are placed near a tooth disc attached on the rotating shaft. The gap between the sensor and the teeth of the disc is very small, so each time a tooth passes near the sensor, it changes the surrounding magnetic field, which will cause the output of the sensor to go either high or low. So the output of the sensor is a square wave signal, which can be easily used for calculating the RPM of the rotating shaft. Thanks for watching, and for more tutorials visit my official website howtomechatronics.com.
Okay, so much about the classical Hall effect, and with this slide I would like to introduce you the family of modern other types of Hall effects. So physically they're usually completely different, but they still carry a name of Hall. So here in this figure you see the classical Hall effect. So you have non-magnetic sample and you apply voltage in this direction, that you will get current. And when you also have magnetic field, then you will get difference in potential between these two contacts, and you can measure it. This is classical Hall effect. If you will take a sample and will put it into huge field of around 10 Tesla and usually low temperatures, a few Kelvin, then you can get to the quantum Hall effect. So it's a very interesting phenomena. We will show it's outside principle of the lecture on spintronics, advanced materials, but we will just say a few words about it. In general, the physics behind is that when field is large and so on, then you will get this cyclotronic motion of electrons here, which should be quantized. It will generate some so-called new Landau levels. And then edge here is very important, because on edge, this quantization doesn't work, so edges are getting conductive in this case. Then we will speak about, let me switch directly to the spin Hall effect. Spin Hall effect, it's an interesting effect, because here you have, again, normal metal, where heavy, usually with large spin orbit interaction, and you send current in this direction. And what happens that electrons with one spin polarization, for example, spin down, are primarily going to one direction, and we will get here spin accumulation. Yeah, so completely another way to get the same spin accumulation like we discussed in the previous lecture. And spin up will be spin accumulated here. So if you will measure voltage in between them, then you will get situations that there is no voltage, will be zero, because the same number of spin up and spin down electrons will be accumulated at different sites. But if you will measure spin dependently spin accumulation, you will see that really you have here electrons with one spin polarization, here it's opposite. I now make step back to the anomalous Hall effect. Anomalous Hall effect, it's in some sense, it's a mixture of these two, of Hall effect and spin Hall effect. The difference is that now you switch your sample from non-magnetic metal conductor to magnetic conductor, and then what you will get enhancement of your Hall effect by the fields created by the magnetization. So it means that you will get still non-zero voltage, like it's in the case of normal Hall effect, but on top you will get also a spin accumulation, so spin-dependent scattering. So here you have features typical for Hall effect and for spin Hall effect together. And then there are next steps. If you go more deep, you can speak about quantum anomalous Hall effect, which should have so magnetic material. And so we see here magnetization, and then you're speaking about spin polarized edge currents, or even quantum spin Hall effect, which should happen as opposite to normal Hall effect without any applied magnetic field. And then you're speaking about opposite direction of spin polarized currents at the edges. But this we will not discuss in the course. Okay, very briefly, what is a quantum Hall effect? So imagine that you have your sample and you placed it at a huge field of around 10 Tesla and low temperature, for example, below 4 Kelvin. Then when you will measure Hall voltage detected across the structure, you will see that it depends from the magnetic field not simply linearly as we expected, but you will get such plateaus, such steps. And in the quantum Hall state, the Hall conductance is precisely quantized in units determined by fundamental constants when material is near to the absolute zero temperature. What are these quanta you can see here? So this will be the quanta of this resistance. So H is a Planck constant, E is a charge of electrons. So you see these are fundamental constants, and N is just an integer. Therefore, quantum Hall effect, first of all, it's very important simply because it proves that we live in a quantum world. And second, it also is of interest for metrology, since it gives a possibility to measure distances very precisely. So that's what I would like to say about quantum Hall effect. And we are coming back now to spintronics. And I would like to start with anomalous Hall effect. Anomalous simply because historically it is happens that anomalous Hall effect was investigated intensively, at least in spintronics field, before spin Hall effect, but we keep in mind that these effects are closely related. So if you want to have, and if you are talking about anomalous Hall effect, then first what we need to do with respect to classical Hall effect is that we replace our non-magnetic conductor with magnetic sample, for example, iron, which has some magnetization. What does it mean? It means that in the simplest word, now your Hall resistivity will have a standard component like for normal Hall effect. So it's the ordinary Hall coefficient. But on top, you add here additional part, which comes from the magnetization of the sample. So in the simplest word, you can say is that you need to take into account field from both externally applied field, but also you need to take into account field created by your sample itself. And then it means that you can enhance the voltage which you detect in the anomalous Hall effect with respect to ordinary Hall effect. So it's interesting how it behaves with respect to the applied magnetic field. So this in A picture, you see the standard behavior of resistivity as a function of applied field. So it's simply linearly increasing, like we have seen in the previous formulas, or you see it also here. If you replace inductance with applied magnetic field H. Now, if you're switching to this panel B, which describes anomalous Hall effect, you see that this behavior is different. And what you can see here is that for small fields, when your ferromagnetic material is not yet magnetized, you remember that there are domain walls, you remember the hysteresis curve, and you need to apply some field that all your moments will be pointing in the same direction. So before it happened, the contribution to the anomalous Hall effect from a magnetization is small. Nevertheless, it's increasing rather fast. So when you increase field, you automatically increase Hall resistivity, but you see that this slope is higher. So it means that you, in addition, you get a more pronounced increase in the resistivity because you magnetize your sample more and more. And then you have this rather sharp slope, but at some point you will fully magnetize your structure. And then the further increase in the magnetic field will not lead to the increase of this component of your Hall resistivity, anomalous Hall resistivity. And it means that afterwards you just have a standard slope given by this component. The only difference that you are already shifted up with the part given by the second component, which is coming due to from the saturation magnetization. Yes, so this is what I would like to tell you about the voltage which we measure in anomalous Hall effect. And now, in order to switch to the spin polarization, to that what is of interest for us, what's going on with polarization of spin, I would like to switch directly to the spin Hall effect. Because in spin Hall effect, it's in some sense it's more pure result. It's easier to understand because in spin Hall effect we are dealing in principally with non-magnetic material, and strictly speaking, you don't need to apply any applied magnetic field. And the effect itself is described here. It's very simple. So when you have such a material, usually you need some heavy metal with a large spin orbit interaction, for example, platinum. And then you apply current, namely that your electrons are moving in that direction. Then depending on the spin polarization of your electrons spin up or spin down, they will be scattered and accumulated at different sides of the sample. So spin up electrons will be accumulated on this side of your structure, and spin down electrons will be accumulated there. So this is in simplest word the spin Hall effect, which is a description is given here. As I said, as a result, spin up electrons will be scattered preferentially in one direction, the spin down electrons preferentially in the opposite directions, both with respect to the current flow and the magnetic spin orientation. So we of course have to take into account all possible spin orientations, but here we're discussing only this electrons which are spin up and spin down. So we choose our axis Z in the direction. And when it was discovered, principally it was also Union studies predicted by Diacono Perel. I think they even have written a book where the term spin Hall effect is used. But it was somehow not noticed by the spintronics community for quite some time. And then spin Hall effect was brought again to attention of the spintronics community by Hirsch. By the way, this is the same Hirsch who has invented Hirsch index, which all scientists pay attention to. And yeah, and since this paper, there was a boom. So many people really study it, since it allows you to get spin accumulation at the lateral boundaries. So the directions of the spins being opposite at the opposite sides. So you remember that we were searching for a way how to create spin polarized current. And the one way was simply to send normal current from magnetic metal to normal metal. And this is used, but it has also its drawbacks. And spin Hall effect, it's a very pure method. You don't need complicated structures. You don't need here multi-layers. You don't need to take into account about how good is your interface. Besides, this is platinum, which to my own experience, platinum is very stable. It has very good adhesion. And once I even I played around and tried to check, it was 10 nanometer platinum also only. There was a sample 3 to 3 millimeter. I placed it on a piece of wood and tried to see at which current I should apply in order to burn it out. And I think at around 1 ampere current, so the wood was already black under the sample, so it was already very high temperature. My substrate broke down, but platinum still was fine. Therefore, platinum is very stable, and you shouldn't worry if you need to work with high current densities. It's very nice one. Okay, and in this slide, I would like to give you the classification of the mechanisms which contribute to spin Hall effect and to that part of anomalous Hall effect, which relates to the generation of spin polarized current transfers to the direction of normal current. So this picture is taken from this nice review of Axel Hoffman about spin Hall effects in metal. And In general, I should say that this field is still developing, and you can find slightly different explanations and models in different papers. But in general, community nowadays agrees that there are three main mechanisms which we should take into account when we speak about these two phenomena. And the first one is named skew scattering. So scattering, it means that we are discussing here a scattering of electron on impurity. And if in the case of presence of large spin orbit coupling in this impurity, you can speak about some effective field gradient in this direction transfers to electric current. And as a result, an electron goes through this gradient of the field, then depending on its spin up or spin down polarization, it will be scattered differently. So let's say spin up electron will be scattered a bit more to the left, and spin down electron will be scattered slightly less. And then in this case, of course, if scattering events takes place many times, then you will get a spin up accumulation this side and spin down accumulation at the opposite side. Side jump mechanism is slightly different. So we again need scattering, we again need spin orbit coupling, but instead of change of the direction of propagation after the scattering event took place, you are speaking about change of the transverse coordinate of your electron during the scattering effect. So let's say when your electron is flying like that, you see after it's left already, it's far away from the scattering effect, the electrons fly along the same trajectory, but they already have coordinates. The spin up electron is already during the scattering, it was slightly shifted to the left side, and spin down electron to the right side, for example, yeah. And then again, if you will repeat the same scattering events many times, you will get situations that many spin up electrons are here and spin down electrons are accumulated on the opposite side. And there is an intrinsic effect, which again is related to spin orbit coupling, but this time we are speaking about its motion and its transverse velocity. So it moves to the left side or to the right side, spin up and spin down in between scattering events. And the reasons behind is here, we need to consider, to explain it properly, we need to consider again the complex band structure of spin-dependent back structure of your element. So these are the three main mechanisms. Just keep them in mind. And with this slide, I would like to present you the inverse spin Hall effect. So this picture is taken from the PhD thesis of Benjamin Fleisch, who defended his thesis in Kaiserslautern. He was investigating this phenomenon intensively. And here you see the simplest sketch of direct spin Hall effect. When we apply current, charge current, so it means spin up, spin down, electrons flying in that direction, and then you see that they are scattered, spin up electrons scattered to the right side and spin down electrons to the left side. That's the easiest way how you can understand spin Hall effect. Now imagine that originally you do not have charge current, but instead you have spin current created, for example, with spin injection, like it was created. Okay, spin injection may be not the best mechanism because you need direct current in that way, like we discussed in the previous lecture. But you can use, for example, spin pumping. And then you will create a source of spin polarized current. So it means that your ideal spin polarized current, as we discussed in the very first lecture, it's when your spin down electron moves in one direction and spin up electron moves in the opposite direction. Then what you have no flow of charge, but instead you have pure and maximized flow of spin angular momentum. And that's exactly what is described here as spin current. When spin down electron moves towards us and spin up electron moves away. Then there is no flow of charge, but there is a flow of spin. And let us have a look what happens if you now put a spin Hall effect on top. This electron with spin up is scattered to the right, exactly like it's shown here. It moves to the right and it's scattered to the right. These electrons if you look on it from the direction how it moves, like here, it should scatter to the left. And when you look, put yourself on that other side, that it moves away from you, it also scatters to the left. But what does it mean? It means that if you have created spin polarized current in such a heavy metal with large spin orbit interaction, you will get a situation that electrons, this and this electrons, will scatter to the same direction. And if they are scattered to the same direction, it means that you will get accumulation of charge already, not spin of electron, but charge. And as a result, you will get charge current. And in this sense, spin-Hall effect is, inverse spin-Hall effect is really fantastic. We also used it a lot in our studies because it's a very good measure for your spin current. So if you want to have spin current, you just send it into a piece of platinum, and then you put voltmeter and you can measure voltage transverse direction. And the voltage range, depending on, of course, on experiment samples and so on, but it varies from nanovolts. And in some experiments, we measured even microvolts, even millivolts, few millivolts. Of course, it was already strongly nonlinear system, but still it can be a very large effect. Okay, then I would like to attract your attention to these formulas. And here we are speaking about electric conductivity XX direction. So this is classical electric conductivity, which is proportional to mobility, as we discussed in the lecture on electric conductivity. And now we introduce parameter of spin-Hall conductivity. Again, it's very similar to the values which we introduce into the when we were discussing about Hall effect, but then we were speaking about resistivity, and here we introduce conductivity which is inversed, but the spin-Hall conductivity is proportional to the mobility, to density, and to the spin-Hall angle. So spin-Hall angle is parameter. You remember there is a Hall angle which defines how strong is your Hall effect is, and here we introduce new parameter spin-Hall angle which defines how pronounced your spin-Hall effect is. And what else is interesting here, that since this electric conductivity it's all about electric charge, you have here charge of electron. Spin-Hall conductivity, it's about spin of electron, which is 1, 2 or minus 1, 2 of Planck constant. Therefore, here we see have no charge anymore, but instead we have Planck constant. So a little remark that you can always understand if this value is about charge or about spin current. And how you can define spin-Hall angle is just a ratio of this spin-Hall conductivity to electric conductivity. And here you have this factor which brings electric word to spin word and vice versa. And then this very simple formula which nicely describe you what is going on. And here you see JS, S stays for spin. So this means that here we speak about spin current. So there is some zero spin current, and the spin current is perpendicular to the applied charge current cross product spin polarization vector. So do not mix the sigma with spin or electric conductivity. That is something completely different. It's a vector which points in the direction of your electric current. So if you, for example, apply the magnetic field, if you perform experiment like spin pumping inverse spin Hall effect, then you usually need to magnetize your sample, you apply some external field, and then the sigma is simply showing you the direction. So it has unique length, just points you direction, and this direction is direction of magnetization in that experiment. Or you can just choose some other selected direction. And the message is very important, this cross product, that when you speak about this kind of effect, you always have to have 3 vectors to be perpendicular. Spin polarization, like here it's pointing up, charge current in that direction, and spin current along. Yeah? So these 3 vectors should be always perpendicular, and the efficiency of your spin Hall effect of generation of your spin current as a function of charge current, like it's given in this formula, is of course defined by the size of spin Hall effect. this theta. And if you speak about inverse spin Hall effect, then you have the same formula, but now you can get value for the charge current as a function of the spin current which you got in your system. And again, cross product staying here. And with the last slide, I would like to show you some materials and to show how pronounced spin Hall effect is in them. And here I use this table from this review where Professor Hoffman has selected values from different papers. And now you can see which materials were considered by the scientific community over the last year. So aluminum, gold, bismuth, niobium, palladium, platinum, tantalum, and tungsten. And here, the most important parameter for us is this spin Hall angle, which is a ratio of these two. So let us have a look. You see, aluminum has very small spin Hall angle. It means that if you want to have a good spin conductor, like copper, that you inject your spin polarized current and it propagates, let's say, 500 nanometers, then you need to use one of these materials, because these materials are known to have very small spin orbit interaction, and therefore spin Hall angle is small. Now, if you will switch to heavy material like this two, then it's known, we have discussed in this the previous lectures, that spin orbit interaction energy is proportional to z to the power of 4, where z is atomic number. And for heavy metals, it's spin orbit interaction is more pronounced. And then if you will look onto the spin Hall angle, this column, you will see that angle is around 1 or 2 degrees, which is 2 orders of magnitude larger than an aluminum. Therefore, spin diffusion length, as we were speaking in spin accumulation, and this lecture will be short here. So let's say 10 nanometers. At the same time, you see that depending on experiment, what kind of experiment you do, how you prepare your platinum, because it all depends strongly on temperature, it depends on the amount of purities. It strongly depends on the interface between different layers. If you use, for example, spin pumping or spin Hall effect, the values can vary a lot. And nevertheless, the order of magnitude, we can get the value. Also very interesting to go to these two material, tantalum and tungsten, because as you can see, the spin Hall angle, these are also good materials with large pronounced spin Hall effect, but angle is getting negative. And this also gives a large advantage. There are many investigations now going on when people try to combine platinum and tantalum to, for example, to enhance the effect. Yeah, like you put batteries, one positive, negative in your pocket lamp, and you have such additional degree of freedom because it's very interesting physics, and we have here the opposite sign of the spin Hall effect. Okay, so much about the family of Hall effects, and I already discussed a few times, mentioned spin transfer torque and spin pumping, and in the coming lecture we will clarify what are these physical phenomena.